Okay, so moving on to the top of page 122. This is our standard parabola, and it is actually the equation of y equals x squared. So in fact, in this particular case, there is an invisible 1 in front of the x squared. Our a value is 1, which actually is telling me that my a value is positive. Now, that is a characteristic that we can keep going forward. So when our a is positive, can you see that my bowl shape actually looks like a smiley face? All right, so we say that this is a happy graph. It's just something to help you realize that your graph will always look happy. Notice, too, that it goes through 0, 0. Now, why is that? Well, if we take y equals x squared as our rule, and we put x equals 0, so we literally replace x with 0, then can you see 0 squared lands up giving you an output value of 0. So your turning point is at 0, 0 for the normal graph y equals ax squared. And again, let's just recap and remember that important characteristic that if I were to take this side, all right, I could actually take this point and reflect it across to there. This point reflected across the y-axis to there. So this point here is 2 units away from the y-axis, and so is that one. So you can see that what we have is a graph which is completely symmetrical about this y-axis. Okay, moving on to the next explanation. Now you can see that what we've got here is a sad face. All right, so that's my face. So we talk about this as being a sad parabola. However, it has come about in this particular case because the a value in this case is a negative 1, and so my a is a negative quantity. So if ever the value in front of x squared is a negative, you are going to find that you have the sad face. Now, can you see that in this particular case, again, my turning point is at 0, 0, but it's actually coming up there and it's a maximum turning point. All right? Now, scooting back to the previous one, can we see here that this is what we would call a minimum turning point? So it comes down to 0 and it comes no lower. So the minimum value that it takes is 0, and then it heads off for the hills again. Right, we are not going to be talking about something like an amplitude in this graph, but what we are definitely going to be talking about is the range. So let's have a look at the range in my happy parabola. Now, I always use a pen or something that I can use horizontally, and if my pen hits my graph at any point, I know that that value must be part of the range. Now, the first time that my pen hits the graph is at 0, so that's the minimum amount. Now, can you see that my graph is actually taking y values all the way? And in fact, as I take this higher, it's going to keep on cutting. So my range, remember, going from lowest, which is 0, up to highest, which is unpredictable, up to infinity. And please remember, I can include 0. I know how big 0 is, but infinity is a concept which I can't include. So my range of this particular graph would be 0 to infinity. On the other graph, let's have a look at what my range would be. Using my same technique, coming from the lowest, can you see I keep on hitting my graph? So all of these y values have been used in creating the graph, but the last time that I actually hit my graph is at 0. If I go any higher, I actually don't hit my graph. So those y values are not part of the range set. So my range in this particular instance is going to be y in element. Remember, lowest is going to come from negative infinity up to the highest value, which is 0. And once again, can you see that this graph is completely symmetrical about the y-axis? This piece would fold over onto that piece almost like an identical twin. We would ask you perhaps to draw y equals 2x squared, and what we would need you to do is to set it up on an axis and to scale it perfectly and to draw for me a parabola. Now, first of all, we do not say, sweetheart, this is a parabola. We want you to recognize that y is equal to 2x squared is actually of the form ax squared. So we want you to have a certain expectation. Right, so let's look. What do we see? Because of the form, it is a parabola. All right? Because a is a positive value, we know that it's a happy parabola. And we know that the minimum value is going to be at 0, 0. And in addition, before we've even put it into any calculator, we know that it's going to be symmetrical about the y-axis. But we want to actually be lazy and we want to put this into our calculator. So we're going to go and we're going to put in y equals 2x squared, and the calculator is going to give us these values. So let's go and confirm it on our calculator. We've got our normal setup and we are wanting to actually go to our table mode, and we are wanting to go to 2x squared. So we're going 2 alpha x, and x squared, remember, is that button, equals. Now remember, when we were doing trig graphs, it was important that we worked with degrees minus 360 to 360. I think it's quite nice to just work 5 units to the left of the y-axis, 5 units to the right, because that gives me a good variety, and I'm going to go in steps of 1. So, off of our calculator, it tells me at minus 5, the corresponding y value is 50. At minus 4, the corresponding y value is 32. At minus 3, the corresponding y value is 18. And just taking that down through to a couple more, you can see at 3, the corresponding value is 18. At 4, 32, etc. So that is how we would get our calculator to do the dirty work for us, to work out the values to be plotted on this graph. Right, we would then draw up our axis, and you can see there that's done for us beautifully. And now what we are going to do is put the points in. Now, starting with 0, 0, that was an important point. Then at minus 1, the graph was at 2. At 1, quite expected, the graph was at 2. So can you see those are reflections? Off of our table, at minus 2, the graph was at 8. And at 2, the graph again was at 8. Now you can see that those values elsewhere in the table, 18, 32, 50, those are really irrational for us, or it's crazy for us to draw our graph as high as that. So this is actually good enough for me to draw the graph of y equals 2x squared. Now you need to take a steady hand, all right? And I normally find that it's best for me if I do the one side and then I do the other. But please make sure, oh, that wasn't that steady, but please make sure that you do not make it angular. Do not use your ruler so that it looks like a V, all right? But try as far as possible not to make this look too drunk or too jagged. Right, let's look at this graph very quickly. Can we see that, again, the turning point in this particular graph has happened at 0, 0. Just in addition, it is a minimum turning point because my graph has been happy. And can you also see that, like we discussed earlier, the range of this graph is going to be from 0 all the way up to infinity. So again, we would talk about the range being from 0 to infinity. Notice too that it's quite a skinny graph. Now the effect of the 2 in this case, do you remember that in the trig graph it actually stretched it out, okay? The effect of the 2 is to actually make the graph quite skinny. Now, while we're on this slide, I just want to show you that if we had drawn y equals plain x squared, it would also have gone through 0, 0, but it would have gone through the point 1, 1. If I inject a 1 in there, out will pop a 1, and it would go through minus 1, 1. All right? And so even if we just draw that piece of the graph, we can see that the graph y equals x squared is very definitely fatter. The arms are this way, whereas the 2x squared, it actually makes it a whole lot skinnier. All right? So the 2 actually affects the rate at which it heads for the skies. Again, it's stretching it. It's making it go much faster than previously.